positive charge, or I can have bigger negative charge. So there's two conflicting things. So there's a point where they might balance out. In fact, there is a point where they will balance out. Always. There's never a case you can give me where the charges are not equal, where there won't be some place where it goes to 0. All right. Now, with that in mind, then, I've got field, 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 field. So in this case, if I put a positive charge, which way does it go? The question is right or left?
As far as
I'm right here.
you're at there, to the right.
Does everybody see that? Because the field is pointing to the right.
Oh.
If I put a positive charge there, it follows the field. What way is the positive charge going here? The left, because the field is going to the left. What way does the positive charge go here? To the right, because the field is to the right. What happens here? It goes to the left because the field is to the left.
Can we do that over?
Yes. All right, so once I've figured out what my field directions are, I can tell you the direction any charge we put there will move, because if it's positive, it goes the way the field points, to the right. It goes the way the field points, to the left. Field points, to the right. Field points, to the left. If I do a negative charge, what happens? Left, because it goes against the field. Negative goes against the field. So the field's to the right, so the negative charge goes to the left. The field's to the left, which way does the negative go? To the right. The field's to the right, which way does the negative go? To the left. Field's to the left, which way does the negative go? To the right. All right, so what happens is once you establish what the field is, positives do what the field says, negatives do the opposite.
How do we know how close or how far it needs to be to change the electric?
Oh, you mean where this goes in?
Yeah.
Bingo, that's what that was about.
Okay.
We just have to solve for it. It's going to be different for every pair of charges.
Okay.
But it's that same approach. Whatever charges you have, you just set the quadratic equation and then take square roots to get rid of them. Got lots of, all right.
Did you say that once you find the field, then the negative does the opposite of?
Right, so once you find the direction of the field, the negative goes the other way. But in every case, what's the magnitude of the force? It's QE. So whatever your Q is, whatever your E is, the force is equal to QE. So once you find what the field is, any charge you put there, you can find the force, because it's just that field times that charge. Whew, are we having fun yet?
You said magnitude of the force?
Once you find the magnitude of the electric field, you can find the magnitude of the force by simply doing this. You're going to have to find the direction from knowing the physics. Do you all understand what I'm saying there? Once you find the magnitude of the field, all right, right, left, so you see whether it goes right or left, to find the direction of, of the force, you have to know the physics to figure it out. So the field is to the right, positive is going to go to the right. If the field's to the right, negative is going to go to the left. So just knowing the field won't tell you the direction if you don't understand the physics. If you know the direction of the field, the direction of the force might be opposite, depending if you've got a positive or negative charge. Okay. All right. So next, we talked about potential energy. All right. So the potential energy is set up anytime we have two charges. We get a potential energy that's simply equal to K, Q1, Q2, divided by R. And this is not a vector. Direction simply does not matter. But for this to be true, what definition did we have to apply to make this a correct expression? That U had to equal 0 at infinity. So this is only true if U equals 0 at infinity. Now it turns out, and I was going to do a little more of a derivation than I have time for, so I'm going to just kind of give this to you because the derivation may not have mattered much anyway. You all heard of voltage in your life? All right. Well, now we're going to find out what voltage is. Voltage is the potential energy per charge. All right. And it leads me to... Notice that these look the same except for not squared, and these look the same except for not squared. All right? So voltage is defined to be KQ over R. Again, only if we define the voltage to be 0 at infinity. Now, here's where it gets a little tricky, is that voltage can be positive or negative, referenced to whether or not you go with or against fields. So V increases along field lines and decreases against field lines. Let's make this easy. Well, can you tell me about the electric field for a positive charge sitting right here? It points away everywhere, right? So if I go from point A to point B, what can you tell me, what happens to the change in the potential or the voltage? It decreases because I go along the field line. Is that going to be a decrease or an increase? All right, I didn't hear the in part. All right, so because I go along the field line, it's going to increase the voltage? Yes. All right. And if I go against it, basically I'm decreasing it. So, yeah.
If we're moving away from A to B, would it be decreasing?
Yeah, I think I misspoke. I've got to think just a second. Let me think that through because my gut level was to say something else. So it's like field. Yeah, it's got to be the opposite. I have to have those backwards. Sorry. No, decreases. Because let's think of it. If I have, if I have the Earth and I've got gravity behaving like this. If I go against it, I'm storing more energy, right? And if this is the energy per charge that we're storing, it's got to go the opposite of what I said. Right, so, but here's the thing. V is completely arbitrary. When we talk about voltage, you have to understand that voltage really doesn't exist. All that exists are voltage differences. If this entire room was 1 million volts, we'd be fine. As long as we didn't leave the room. All right, so being at a particular voltage doesn't mean anything. It's when you're at a voltage and something else is at a different voltage, that's where you're in trouble. All right, but if everything's at the same voltage, it's 0, 10, 1 million, doesn't matter. Right, voltage only matters as we move with or against the field. I mean to a different potential or a different voltage. In a strange quirk of physics, this is one of the only times this happens. This is the quantity and this is the unit. And they're not the same. All right, it's be like mass equals free mass. And that, if we wrote that for kilogram, it'd be the same symbol. Don't let this confuse you. Well, ask if you're, but clearly that doesn't make any sense to say that V equals 10V because that's mathematically idiotic. So this is basically saying that voltage is equal to 10 volts. All right, and when we say that, it's always considered to be a change in voltage. So this is frequently done, and I will probably try to do it often when we're doing things. Rather than just saying V is equal to that, we'll say delta V is equal to that, and then it clears up any problem. The change in the voltage is 10 volts. All right, and that what we're going to do in our lab today is actually a little bit ahead of where we're talking, but it's tied to some of these ideas. So, yeah, let me see if there's any. I'll just have to double talk on Wednesday. I'll cover some of these. So the thing to remember about voltage and potential, they're not vectors, they're scalars, so you don't have to worry about direction at all. On potential, how do I know when this is a positive number? When did you do a positive number? When both charges are the same. So two positive and two negatives that have a positive potential. If they're different, one positive, one negative, then it's always a negative number. All right? So you don't have, you can put, on this one you can actually put the signs in and it'll work out. If you have two negatives, it multiplies to positive, two positive, fine, positive and negative will go negative. Same kind of thing goes here. A positive charge has a positive potential, a negative charge has a negative potential. I'll talk more about that down in the lab, so I'll see you down there in 10 minutes.
So, line that you're looking at.
Uh-huh.
Negative is on
Well, there's still, oh, guys, so he's actually, field is everywhere. You give me a charge, there's a field in every direction and everywhere in the whole universe. There's not just one line of field.
right, what we're talking about.
On that line,